There is something we've kind of skipped over that deserves discussing. We talked about resistivity in the previous video and how it's connected to resistance. Well, it turns out the resistivity of a material changes depending on the temperature of that material. In fact, it changes non-linearly. But one way to model the change in practice is with the following equation below, with the temperature changing linearly. Let's try to break down what's going on here. Rho naught is just the measured resistivity at some temperature T naught, and alpha is what's called the temperature coefficient of resistivity, which changes depending on what kind of material you're working with. This means we're assuming the resistivity rho has a linear dependence on temperature. It increases linearly as temperature increases over a large range of temperatures. Now, it's easy to see that this model has its limitations. Namely, it has a pretty big tendency to break down specifically near really low temperatures, close to absolute zero. If we're looking at a normal metal conductor, like gold or silver or copper, as the temperature approaches zero, the resistivity tends to converge to some non-zero value. Which kind of makes some sense. We wouldn't really expect the resistivity to ever be zero for any material, right?
Wrong!
It turns out there's this fascinating phenomenon in nature called superconductivity. Superconductivity gives rise to a wide array of interesting effects, but we're going to focus on only one of these, the zero resistivity one. Now the curve we saw before applies to a huge amount of materials, but some materials behave like this instead. As we drop the temperature, the resistivity is going, and then all of a sudden, wham! The resistivity discontinuously drops to zero. Remember also the resistivity dropping to zero is equivalent to the conductivity becoming infinite, hence the name superconductivity. Think about what this means though. It means you can effectively induce an electric field across a conductor to create a current. We'll show how later. Remove the electric field, and the current would just keep going on and on and on with no energy loss, because there's no resistance in the conductor.
2,000 years later.
Super bizarre if you really think about it. We call this temperature at the discontinuity the critical temperature, or T sub C, and it tends to be very close to absolute zero, usually between 0 and 10 Kelvin for naturally occurring superconductors. Over time, though, humans have searched for more and more superconductors, and for some artificial materials, their critical temperatures can be much higher, say between around 10 and 100 Kelvin. Still really cold and nowhere near room temperature, which is around 273 Kelvin, but it's a start, isn't it? It's likely that if a material were ever discovered that had superconductivity very close to room temperature, it would totally revolutionize the energy industry as we know it.